Hi, good morning.
Good morning, ma'am.
Yes. Okay. So in the so far we discussed about a mixed design based on IS methods. Fine. I hope your exams are fine. You won't have any issue in that. Okay. In the last class, I forgot to mention this. I have as a workout example, so you can go through or work out this problem when you are free, if you are interested, because I'm not going to count this. Fine. So in today's class, we will look at how to do concrete mix design based on ACI method. So by now you're familiar with how to do mix design based on IS methods. I hope you have the mix design code standard for IS method, right? So all of you have the IS code 10262.
Yes, ma'am.
Okay. So this ACI code, this is licensed code, and I'm not allowed to share that code, and that's why I have just taken a screenshot of that and included all the data whatever that is required for mix design in this PPT. So I don't know whether you can find or download this code by yourself. So similar to IS method, ACI method also needs specific conditions for starting out. Just do this mix design. So of course you need to know maximum water content or water cementitious ratio, and then minimum cement content to be used, and what would be the air content in that, and what would be the required workability or the slump, and what would be the maximum size of aggregates to be used for that particular applications, and the strength requirement. In addition to that, other parameters factors that could affect the mix design. So you may use admixtures, or you may use different types of cement or cementitious materials or different types of aggregates. So these are general things that you already know when we talk about mix design. So there will be slight difference in the mix design comparing to IS method. In IS method, first step itself, you should know the target strength, and then the second step is to estimate the air content, and then you will come up with the water cement ratio. So here, first step is you should find out your slump value. If it is given, then it is fine. If the slump value is not specified, the code has recommended to use a slump for different applications. So if your construction is going to be a foundation walls or footings or beam and reinforced walls or building columns, then the minimum and maximum required sum will be this. If the client or the constructor is not specified the required slump values, then you can choose this slump value depending on the type of construction you would be using. Fine. And here, this slump value, again, you should note that this is for meeting this particular construction. If you expect, and this is for when you use vibration for consolidation. So typically, while concreting after mixing, so we place the concrete in the formwork. So while placing the concrete in the formwork, we do consolidate or compact the structure so that that will release any entrapped air, and your matrix will be link. So for that we use different types of vibrations. In the next classes or in the next lecture, we will be looking about this handling of concrete during mixing and placing those things. So just to have an idea about these vibrations, we will do different types of vibrating systems. Certain places you do using rod, you do vibrations. That is typically manual vibrations. You can just hold rod and damp the concrete. And in other ways, you have needle vibrations. You can place the needle and you can use that vibration to compact. And there are table vibrations, and there are certain different types of vibrations available for consolidating the concrete. So this is for based on the vibration. If you are compacting, you can use these values. And sometimes when you are using chemical admixtures, then the slump may vary. So you should have an idea or you should give care when you use chemical admixtures, the slump value not change much or it should be adequate to avoid segregations or any bleeding in your concrete. Again, if there are other methods, if you use other methods than this vibration, then your slump can be increased by 25 mm. And the second step is to know the maximum size of aggregate, and you know the importance why you should have the maximum size of aggregate limit for particular applications, because if your aggregate size is too low, then that may be congested for placing your concrete, especially when you have reinforcing steel and pre-tension ducts where the space between the steel and the ducts will be limited. So in that case, you should have a control on your maximum size of aggregates. So these in detail we looked in the aggregate portions where it clearly specifies depending on the size of the member what should be the maximum size of aggregate to be used. I hope you remember this. So accordingly, when high strength concrete used, you should play with your size of aggregates. So minimize or the size of aggregate as much as possible so that it provides high strength at a given water cement ratio. You might have in the IS method we looked at target strength. Similarly here we look at average strength. Okay. So if the values are given, so typically here in this case, the standard deviations will be given based on the laboratory conditions or test results. If not, you can choose the standard deviation depending on your conditions. So IACA has specified the. By now, you are familiar with this formula. So what is FCK, what is the FM and KS? So KS is the probability factor, risk factor, and then S is the standard deviation. So depending on your conditions, you can choose your probability factor, and this allows your probability strength below. So if you are testing 1 in 6 sample, 1 in 20 sample, or 1 in 40, if you are allowing one sample in 6 to fail, then you can choose this. If you are allowing 1 in 20, then you can choose this. So depending on the probability factor may vary. So in detail about this, we will look when we discuss about testing of concrete. And now you just be aware of the, how to choose the standard deviation depending on the number of tests that we do. So typically, codes specify to you get the standard deviation from about 30 samples. So if you want to know the standard deviation for particular mix, then you should do testing for 30 samples and take average of that, and then you can find out the standard deviation from the 30 samples. So in that case, your factor for standard deviation becomes 1. But in case you do not have enough sample to test and you can only have 25 samples, then this factor increases. And if you are using only 20 samples to get the standard deviation, then this will be corrected. And if you are using only 50 numbers of samples for obtaining this, then this has to be corrected. So typically, we have this limit of, or we have the specifications to get the standard deviation out of 30 samples. So in that case, this becomes your average compressive strength at 28 days. And this is your design specified value, and this will be the depending on the concrete strength that is required, you can choose the values here, and you should choose the higher of these two. So this is similar to what you saw in a target strength, but the number of values will be slightly different. Why? Because in IS method we generally use cubes. cubes, right? In ACI method, we test cylinders. So there are like when you change the specimen geometry, then the compressive strength will also vary. Okay, so the compressive strength depends on the geometry of the specimen also. So this in detail we will discuss when we discuss about the testing and the hard and properties of concrete. But here to get the basic difference, you should know where the compressive strength of cylindrical specimen will be about. So if you are testing, 1 second. So cylindrical specimen will have less strength comparing to cube specimens for the same grade of concrete. Okay, so typically the cylindrical strength is 0.8 times the cube strength. What is this? So you have to do those corrections when you are adapting this method for our conditions. That's why the ACA method is not suitable for the specific international codes or the specifically designed for the practices and the materials that is locally available there. So sometimes we cannot use directly in such situations. So what we have to do, we have to do those correction factors, especially the properties for aggregates and the cements will have huge difference between what we use here and what is being used there. So especially this is one such difference there. The cylindrical compressive strength is used, but here we use cube compressive strength. So when you adapt this method, you should have the conversion to take care of this. So finally, the point here is
Ma'am,
sorry.
ma'am, is it 0.9 or 0.8?
0.8. So wait, I'll just fix my pen. It is not writing where I'm placing it. That is 0.8. Just give me a few minutes. I'll just fix this. So cylindrical compressive strength will be about 0.8 FC. So you have to do those corrections when you adapt to the CSA method. And here, then after finding out the average compressive strength for a given grade of concrete, you can choose your water content. So estimation of mixing water and the air content. So here you know what will be the required slump conditions and the maximum aggregate size that is used. So these are the these information that's from step 1 and step 2. So based on that, you can find your water content required for non-air entrained concrete. So that is normal concrete, and air entrained concrete is something where you have where you purposefully introduce some amount of air. So for both cases, the specifications required for getting the water content is given. So if your slump requirement is about 70 to 100 for using 12.5 mm aggregate, then your required water content will be 216. Whereas if you go for air content for the same requirement, your water content will be less, because in general when you have more air in the concrete, especially in trying years, then the required water content will be less. So this is the basic difference. But here in this case, we will have some amount of entrapped air content. So that is different. So from that you can get the required water content, and you can go through these correction factors. This basically gives the values if your aggregate size changes or if the type of aggregate changes, what will be the corrections required. Similarly, what we saw in IS method. So once you know the water content requirement, you can select the water cement ratio or water cementitious material for by knowing the compressive strength at 20 days. So this value you got from step 2, that is the average compressive strength, and now you know. So from that you can get the water cement ratio that is given for non-air entrained and for air entrained. So whereas in this IS method, you have a curve that's specified for the target compressive strength. So you can, based on the compressive strength and the type of cement used, you can choose your water cement ratio from the plot. But here it is given in table form, specifically for a non-air entrained and air entrained concrete. So you can see here the is concrete strength. So these strength values are based on the size concrete cylinders, moist cured for 28 days. Again, these are some correction factors that you can choose when the curing conditions or other conditions changes. And depending on the exposure conditions or the type of structure, there is a limit maximum permissible water cement ratio, especially for this severe exposure. So this can also you can go through. Finding, I'm not getting into the details. Now here to get the, so if you have to just use wall cement, then it is fine. But if you are using any pozzolanic material, then you can find out the required water content or the amount of pozzolanic materials fractions by using this formula. So there are two approaches. One is using the weight, equivalent weight. The second approach is to the equivalent absolute volume. Here the concept is the table value whatever that is given. So if you are using pozzolanic material, basically we are equating both as same. So we don't know how much cementitious material to be used in that case if pozzolanic material is used, but whatever that ratio that we are getting, that we are equating to this water to sum of cementitious cement plus pozzolanic materials, right? So from this, we are basically trying to come up with the relations that we can obtain the required whatever. If you want to cement content, you can get this. So this FW represents the amount of pozzolanic material to be added in the matrix. So for example, if you are planning to add 20% of pozzolanic material, then the FW value becomes 0.2. Okay, so that value is, it's a proportion to this. So the pozzolanic material, and you have this TP relationship. So you can find out either cement content or Either you can get the post-organic materials content. So by substituting this in this value, you can find out the cement content values. Suppose if this replacement is not given by weight, but it is given by volume. So in that case, you can use this formula where you can get the replacement level by using the volume content. So the FW is basically the post-organic material percentage by weight, and P value is the weight of post-organic materials, and C is weight of cement. So if this replacement is given in terms of weight, this equation will be used to obtain these parameters. And if the given term is in terms of absolute volume, then you have to use these equations where you use the specific gravity so that you can come up with this weight calculation. When you know the second approach, you can get this instead of here you are equating this water to cementitious ratio to water to cement ratio, and then by using these factors you can come up with the individual calculation for cement and for organic materials. Whereas in this case you are equating this to the volume itself. So for that you have to use this equation, and from this you can compute the separate cement or post-organic content. Fine. So now you know what would be the required water content from the step 3, and then water cement ratio you know. So from that you can calculate the required cement and post-organic materials. And here almost all the steps will be similar till calculating cement content, and then it gives two approach to get the post-organic material when the post-organic material is added in the concrete matrix. So in such cases, you have to approach. One is by using equivalent weight, another one is by using equivalent volume. And then the next step is to find out the volume of or the weight of coarse aggregates to be added. So in the IS method, you after finding out the required or the estimated cement content, you will come up with the proportion we used for coarse aggregate and fine aggregate, and from that you will estimate the volume of coarse aggregate and fine aggregate, and then you calculate the mass of coarse aggregate and fine aggregate. Here you can directly get the coarse aggregate of weight or volume. You know that you got the value of water, you got the value of cement, you got the value of coarse aggregate, and you are not aware of how much to be a fine aggregate, the weight of fine aggregate or the volume of fine aggregate. So only that parameter will be left unknown, remaining all you know by the end of that step. So for that, here it has a simple approach where by knowing the density of concrete, you can estimate the fine aggregates value. One second, it is loading. Okay. So now you can estimate the course aggregate values. Here, knowing the main nominal maximum size of aggregate, and here you use something called dry roded density. So that means you find out the density based on the dry aggregates, and then while weighing the aggregates, you will be following certain procedure. So the standard procedure says the aggregate in the known weight of a standard container, aggregate has to be placed in 3 layers, and each layer has to be tamped by rod for about 25 times. Okay, so the each layer will be tamped by 20 by rod 25 times, and then the layers will be filled and the weight will be taken and you get the density, and basically the density is called dry roded density. So here the cases will also be given for that particular density of coarse aggregate. So you will get the volume of dry roded coarse aggregate using the fineness modulus of fine aggregate. So these values will be given. So what would be the fineness modulus that will be of your fine aggregates to be used? So knowing that, you can get the volume of coarse aggregate at this stage itself. So now you have to find out the estimation of fine aggregate. To find out the estimation of fine aggregates, you have to calculate the density of fresh concrete. So by knowing the maximum size of aggregates to be used, you can estimate the concrete density, that is kg per meter cube. So for non-entrained and air-entrained concrete. So if this is not given, you can also use this equation to get the density. So if the aggregate value is not specified, so then you can use this equation to get your density of concrete. So what is the density of concrete? You can find out the volumes of or the weight of other ingredients, and then you can subtract that with the total weight of the ingredients in the concrete matrix. You will get the weight of fine aggregate. And then water adjustments you will be doing in a similar way what you did using IS method. So since I do not have much time, I'll just quickly go through these example problem that is from ACA code. So that will give you an understanding how to use this ACA specifications for concrete mix design. So here in this example, you are asked to design the concrete strength whose average strength is 24 MPa. So note here average strength is just given. So with the slump value of 75 to 100 mm and the coarse aggregate size is given 37.5 and the dry roded mass is given 1600 kg per meter cube. So other ingredients, specific gravity of cement is given, and then the specific gravity of coarse aggregate is given, and the water absorption capacity for the coarse aggregate and fine aggregate is given. So 0.5 for coarse aggregate, and for fine aggregate it is 0.7, and the fineness modulus is also given as 2.8. So here the first step is to identify the slump value. In this problem, slump value is given as 75 to 100 mm. So we know the range of slump here, and then the maximum size of aggregate is given. So you know the maximum size of aggregate that you will be using in this concrete. So now this is for there is no specification for air entrant concrete. So in that case, this would be for non-air entrant concrete. So you can choose the water cement required water content from the table for this slump value size of aggregate. So for that given slump range and given range of maximum size of aggregate, the required water content is about 181 kg per meter cube. Fine. The step 4 is to identify the water cement ratio for non-air entrant concrete with a strength of about 24 MPa. So So this is direct problem because there is no pozzolanic materials here. So you can directly get this water cement ratio from the for this particular strength of concrete, that is 0.62. So you can use the table to get this water cement ratio. So you know your water cement ratio now, that is 0.62, and from that you can calculate your cement content. So the cement content would be 0.62. You have to divide that 181 by 0.62, you will get your cement content, right? And then you have to estimate the coarse aggregate content. So from the table, for the finest fine and aggregate having a modulus of 2.8 and the nominal maximum size is 37.5, for that, what would be the required estimated coarse aggregate? So you can come here for the 37.5 and 2.8, you have your volume of dry roded coarse aggregate per unit volume of concrete is 0.71. So that indicates that the volume of coarse aggregate is 0.71 meter cube. So from this you can get the mass of coarse aggregate because you know the dry order density. So dry order density is 1600. So by multiplying coarse aggregate, you know the weight of coarse aggregate to be added in the concrete. So now you know all the values in terms of weight. So you can, but everything is in per meter cube. So you can convert that for required size of the specimens that you are using. So you can get the exact weight that is required. So remember all the methods using IS method and ACA method, you get your ingredients or values per meter cube. So when you are calculating the required mass or weight to be taken for particular concrete batch, you should know the geometry of the specimen and you should know the number of specimens to be casted, and then you can calculate the total volume and you can multiply the volume with this kg per meter cube value, so you get the actual amount of cement or water to be added in the matrix. And sometimes we keep 20% as a factor. So we will have that factor so that we will have some excess amount of cement. In case if it is required, we can have in addition. So generally when we do mix design and when we take that mixes for when we take weight for mixes, we take 15 to 20% wastage we will consider, so that after wastage we will have enough material for filling the required samples. So I think this got stuck. Yeah, sorry, that is not slideshow is not working. So I'll just show here itself. So this will be fine. In that case, from that step, from the sixth step, you know how much amount of force aggregate has to be added. From that, you can estimate the amount of fine aggregates because you know the quantity of water, cement, and coarse aggregates to be added, and the remaining material is only the fine and then entrapped air. Okay, so you can subtract those things here. So now here you can see the weight of water and the weight of cement, and you know the weight of coarse aggregate. And for non-entrined concrete, you have to calculate the density of concrete, fresh concrete. And for this particular grade, here you can see in this table, from first estimate of concrete unit mass kg per meter cube for 37.5 is 2410 for non-air entrained concrete. So you have your density here, and from that, you know the calculated weight for other ingredients. Sum of this water, cement, and coarse aggregate will be this, and you have to subtract this from this to get the fine aggregate, and you have to subtract the entrapped air content also. So by doing so, you mass of fine aggregates here. So it's very simple method. You have to just get the weight of other ingredients using the procedures, and then final fine aggregate can be obtained by calculating the density of water, density of concrete. So you know density of concrete, you know weight of other materials, and you can subtract the weight of other materials from the unit weight of the concrete. You will get the weight of fine aggregates. So if it is per meter cube, then it will be a meter cube. So for 1 meter cube, you will get 801 kg of fine aggregates. So that is based on mass, but if you want to go with based on volume, you can calculate volume also. You can calculate the volume of water, you will get in meter cube because we are designing all these things for 1 meter cube. So if you know the volume of other materials, again the similar way, you can subtract some of the volume of other materials from the unit volume of concrete. So some volume of water and then volume of cement can be obtained, and volume of coarse aggregates because you know the mass of coarse aggregates, and volume of entrapped air you can get because mass of entrapped air is not possible to get. That's why it was not included in the weight calculation, but in the volume calculation, volume of entrapped air, because the code has specified the volume for entrapped air, and you can add all those things and subtract that from the unit volume. You will get the volume of fine aggregates. So with this, you can end up with your basic calculations. You know your trial mix is ready, knowing the weight or the volume of each ingredients to be added in the matrix. So this gives a comparison of the water and cement coarse aggregates and sand when you use the weight-based calculation and when you use this volume-based calculations. And that's it. I just want to show this so it because you are very familiar with IS method. So this is slightly different from IS method. The main thing you have to um, consider is the compressive strength of concrete because here compressive strength is based on cylindrical specimens, whereas in IS method compressive strength is based on cube specimens. So those corrections have to be taken. Other than that, the procedure is almost similar except the estimation of coarse and fine aggregates. There, the estimation of coarse and fine aggregates is calculated based on the proportions. Here, it is calculated based on it is calculated individually. When you know your dry order density and fineness modulus of fine aggregates, you can estimate the volume of coarse aggregate. And once you know the volume or mass of coarse aggregate, and before that step, you know the mass of water and cement, and from that you can calculate the volume also corresponding to those. So knowing that, you can come up with end up calculating the fineness aggregate by calculating the unit density of fresh concrete. So if you know the density of fresh concrete, you know the mass of fresh concrete. So knowing the mass of fresh concrete, you can calculate the fineness fine aggregate mass by subtracting sum of other ingredients from the mass of concrete. Whereas when you use this volume based calculation, you have to subtract the volume of other ingredients from the unit volume of concrete, because all these ingredients are calculated, this mass are estimated per unit volume. So both ways you will get similar results. In unit volume calculation based on volume, you will include the entrapped air calculations also, whereas when you use that based on mass, you may not include entrapped air, because getting mass for entrapped air is difficult. That's why in IS method, after calculating the what cement content, you will change everything in terms of volume, and then you get the proportion based calculation for coarse and fine aggregates. Then you for the coarse and fine aggregates, and then you calculate the mass of coarse and fine aggregates. So these are some basic differences when you use final, when you use IS and ACA method. So you can go through this example. It is very simple and easily understandable. So I have given couple of example problems. So those who are interested, you can work out this. So based on this ACA method, and you can try this based on IS method as well, because the data is common for both. It is all about how you are following the steps to estimate the final outcomes. So here I just want to emphasize few details in this problem. You have average compressive strength, right? Average compressive strength is given, and you know the maximum size of aggregates, and dry order bulk density is given, and specific gravities and water corrections, water moisture, those things are also given. Yeah, here I forgot to mention the water correction here. So the water correction is similar to what you follow for IS method. So just if your aggregate is wet, you just calculate the mass of wet aggregate and you subtract that with the SSD condition. Then you get your water correction. And here the strength specified is 20 MPa at 28 days, but it is not average compressive strength. But here the data is given that specified strength is 20 MPa. Sorry. The average value is given for one test results into 1 in 2 condition is given. So in that case, in the table, it shows the standard deviation to be considered for this 1 in 20 cases. You can use that to calculate the average compressive strength using the equation given in the previous slides. And other than that, other conditions are similar. You can same steps to get the estimation of proportions. If there is anything not clear, or if you want to clarify any specific points in this method, in the next class you please let me know, because now I feel I haven't covered properly because my file is not working well, so I kind of interrupted my flow also. So since you're familiar with IS method, this method will be very simple to follow. So I have mentioned all the steps here. So you can go through this. I will share this slide now, and you can work out these problems as well. Is it clear?
Yes, ma'am.
Okay, then we'll meet on Monday.
Thank you.
Yeah, thank you.